But Catherine, it's a really great pleasure to invite you to talk. So we really look forward to your talk. I'll hand over to you.
Thank you so much, Josie. Let me just get my slides shared and arrange things. So can you hear me and see me and see my slides?
Yes, that is perfect. That is great.
Oh, right.
Thank you very much.
Just what I wanted here. All right. Thank you so much, Josie, for that nice summary of this morning's talks. That's really thoughtful and helps us all remember what we saw. My name is Catherine Kuchenbecker. I'm a director here at the Max Planck Institute for Intelligent Systems, and it's my pleasure to give this plenary talk to tell you a bit about research that my team is doing. I grew up, although my name sounds German, I'm actually American, and I grew up in Los Angeles. I did all my studies, all my degrees in mechanical engineering at Stanford University. And I did a brief postdoc at Johns Hopkins with tomorrow afternoon's plenary speaker, Alison Okamura. So you should definitely go to her talk and all the other plenaries. It's really a delightful set of speakers you put together. And after I did that short postdoc with Alison, I started my faculty career at Penn at the University of Pennsylvania as part of the GRASP lab. And I chose to go to Penn because it had this interdisciplinary spirit. It was in the engineering school between mechanical engineering, electrical engineering, computer science, and biomedical engineering. We had lots of connections to neuroscience and psychology, and they really transformed how I thought about research and what it meant to be doing interdisciplinary research in embodied intelligence, in robotics, in AI. And in January of 2017, so a little more than 5 years ago, I moved across the Atlantic to the Max Planck Institute for Intelligent Systems. This is a map of Germany. We're here in the southern part of Germany. I work in Stuttgart, and we have another site in Tübingen. Our institute is quite young. We were only founded 11 years ago, and it's a big institution. We are extremely lucky to get generous taxpayer-funded research money for research in all areas of intelligent systems, which I think overlaps very, very well with the spirit of this conference. So our institute is composed, we have directors at the top. So these are like the endowed full professors who we stay here for the rest of our career. We have a wonderful set of group leaders who work here for like 5 to 7 to 9 years and then go out and get a professorship somewhere else. And maybe in your field, you know some of my colleagues, maybe you know Michael, Moritz, Bernhard, Christoph, or Metin, or some of our group leaders. This region we call Cyber Valley, and there's really a lot of investments here, and it's a really exciting place to work. I want to mention we are hiring at all levels. So if you know someone who's looking for an internship or someone who's looking for a PhD position, a postdoc position, we're probably going to be hiring more than 10 group leaders over the next few years, and we have 2 director positions open as well. So if you're interested in exploring opportunities in our institute, please reach out to me or any of the other directors, anyone else here. And we have things going on in the whole spectrum of things you might see here. But now we'll focus in more on what I do. So like I said, I work in Stuttgart. That's more where the physical aspects of intelligence are being explored. In our institute in Tübingen is more the computational side. And my team, I have about 30 to 35 people working with me. I have 15 PhD students, postdocs, some postdocs who recently got faculty jobs, and we're still finishing up, some central staff. We always have lots of visitors, interns visiting PhD students. It's a very diverse group, not only in the fact that they come from many different backgrounds and from around the world, but we're working on this topic of haptic intelligence, the name of my department, from many different angles. And I wanted to give you a little bit of a perspective for that before I dive in deeper on the central topic for my talk today. But below all the work that we're doing, I would say the main underlying motivation, like what we're most curious about and what we're really driven to try to understand and take advantage of, is the sense of touch. And your sense of touch is really important for humans, also for animals, but I know a lot more about humans than I know about animals or plants. Touch is our first sense to evolve, and it's very rare, but if you do happen to lose your sense of touch, it makes life extremely difficult. And that's because touch is the feedback system of your sensor motor system. And so it's deeply coupled to physical actions and also to social interactions. So I want to reach out and pick up this glass of water. Touch is involved in how I move my body, how I come into contact with the world, how I stay safe, how I interact with other people, how I feed myself. And it's spread throughout your body. Unlike your eyes and your ears, which are very localized organs of perception, your skin is a huge organ and has many, many different channels. And so When I talk about your haptic perception capabilities, I usually split it into your tactile system and your kinesthetic system. Some people call tactile cutaneous. This is everything that's actually in your skin, so wrapping you all around your body at the interface between you and the rest of the world. And the mechanoreceptors that are embedded in your skin give you the ability to sense where contact is happening, how it's pressing, is it stretching your skin, are things slipping across your skin, is something vibrating against you, is a tool that you're holding vibrating as it hits something, as it cuts, is your skin changing temperature, is heat being added or removed from your body. And we have a little bit of proximity sensing in terms of hair follicles on the hairy skin. It's also really important to understand that skin is not uniform. So the skin all over your body is adapted to the location. And so the number of receptors at the tips of your fingers is higher than at the next area of your fingers, and then the other areas on your palms. And that's the glabrous skin that's also is very finely tuned. And then the hairy skin is more broader receptive fields, and it's not as densely innervated. And even among that, different regions of your body have different levels of sensitivity. And so there's a lot to know, but that's probably a good start. Your kinesthetic system, or also involved in proprioception, is knowledge of how your body is moving in space. And so this comes from, you can feel, not consciously, but subconsciously, the lengths and velocities of your muscles, the forces in your tendons and ligaments, and the angles of your joint receptors. And robots, like a robot we design and build, would tend to more have sensors like this, and not so much of these tactile sensors. And I think tactile sensation and feedback represents a huge uncapitalized on opportunity for robotics and general technology. And so this is what I'm really fascinated in, and hopefully get you excited about it today through my talk. So if the sense of touch is so important to humans, you might wonder why then so many engineered systems that we interact with each day, they basically ignore the user's sense of touch, or the sense of touch of the system. What do I mean by that? I think if computers could draw a picture of what users are like, they have an eye, maybe they have two, probably just one, they see visual stimuli. You can hear things, and maybe there's a hand, or maybe it's just an index finger. My iPhone can feel when I touch it, which is good, but it never presents programmable sensations to me. I pet my cat, Toby, or feel fabric of something I'm shopping for online, and it always just feels like glass. We don't have digital display of haptic sensations on screens or in virtual reality. Systems can measure my motion, but they don't present sensation. So that those digital virtual interactions that we can have are very different from the physical interactions we have in the world. This also happens when people are remote controlling robots, say for robotic surgery, which is a topic I've worked on a lot. I can see very well inside the patient. These robots are being used right now around the world to operate, to remove prostates and do other minimally invasive procedures. But the surgeon cannot feel what they're touching. They can only see. And that's very different from manual interaction, from open surgery. And I think it's part of why this technology hasn't delivered on the promises that everyone thought, oh, it's the future, but you can't feel. You should be able to feel in the future. If we then turn to robots more as autonomous agents or semi-autonomous agents, they also lack haptic sensation. I'll talk more about this, even when, and especially when they're there to interact with people. They're basically numb all over, no sense of touch. People have a really hard time functioning with no sense of touch, but we give our robots almost no sense of touch. So my mission as a researcher these days, I would say it very succinctly, to try to bring physical interaction and touch cues more to the forefront in all these different engineered systems, whether that's feedback for humans or endowing robots with a good sense of touch so that they can more capably interact with the everyday world, which is unstructured and messy and has people in it. So my team, we work in 5 main fields. There are a lot of overlaps between them, but at the basic level, we're often looking at how fingertips function, what you can feel. The mechanics of soft frictional contact are fascinating. We use some of that knowledge to design and refine and characterize haptic devices, which you'll hear more about in Allison's talk, but are mechatronic systems that create sensations for people to feel, either from a virtual world or from a remote environment when you're controlling a robot. We work a lot on this, how to add haptic feedback as a user is controlling a robot remotely, how to understand their skill learning over time, how they can train, how they can improve more quickly. Can we automatically assess their skill? And then now turning more to where robots are an agent, we've also been doing a lot of work in physical human robot interaction. And then at the end, touch sensing, inventing new touch sensors. And it's these last two fields that I wanted to focus on, that I was asked to focus on in this talk today. So touch sensing and physical human robot interaction. And I find there's a really virtuous cycle between these two, because if we can come up with new touch sensors, there are very few good touch sensors in the world. We need more. But if we can come up with new approaches to touch sensing, then we can create new ways for humans and robots to interact together. And also on our needs side, or maybe there's some kind of interaction we want to create, we can come back to the sensor engineers and say, oh, we need different kinds of tactile sensors than have been invented so far or than are available. And maybe we can create something that's more like this, and that can let us do what we want. And so I'll be talking about several projects in this domain today. I got started in this. I did my PhD in haptics and teleoperation, but then my first PhD student at Penn, Joe Romano, he wanted to work in autonomous robots. It's something big at GRASP, and I was also interested in this. And we were lucky enough to get a PR2, a personal robot 2, which is a bimanual mobile manipulator from Willow Garage, which doesn't exist anymore. And he did an internship at Willow Garage, and we did a project with some people there where we wanted the robot to be able to pick up all kinds of different objects, no matter what they were, and without having to know ahead of time what they were. And we took a lot of inspiration from neuroscience. This is a beautiful paper, probably my favorite paper, by Johansson and Flanagan, about the beautiful coordination of how the tactile receptors in fingers coordinate as you close and you feel contact, and then you lift. And then if something bumps you, how you react, or if you're setting it down, you don't move the glass right to the surface of the table and let go. You move down till you feel the contact, and then you let go at that moment. And so we tried to endow the PR2 with similar kinds of AC, like event-based signals and steady-state signals, just based on its very, very rudimentary tactile sensors, which were just a very low-res 3x5 grid of pressure cells, which were very hysteretic and low sampling rate, like 24 hertz, if I remember, plus an accelerometer. And that accelerometer was really important because it's like a shock sensor. It's a high bandwidth vibration sensor. So that would let us feel, if I'm holding an object and I'm moving it down, you can feel like, let's see, a transient when the object hits the table. Or in the pressure sensors, we could look at the high pass filtered version of the pressure signal and know that something had slipped and the robot should hold on tighter. Or if we're handing the object over, something had slipped and it's time to let go. And we found, even though the sensors were quite rudimentary, we could do a lot. This is a video of picking up and setting back down some objects where the robot doesn't know what they are. We also did use this capability, the accelerometer, for high fives and fist bumps, which is lots of fun, but basically the robot's just moving through a trajectory and waiting till it feels the contact. I won't talk about this more today because today is not about accelerometers, but about tactile sensing. Okay, so then we'd done that project with the PR2 and we wanted to do more. And I was working with Trevor Darrell on a DARPA project where we had to teach the robot perceptually grounded haptic adjectives. We wanted the robot to be able to touch things and not just pick it up and set it down, but to be able to feel it and describe it in words like a person would. So here's our vocabulary of adjectives, and we had the robot touch objects in different ways. But the sensors we had, which you can still see here, are nowhere good enough to get any sort of perceptual impression of the objects. So we endowed our robot with these biotacs, which were and still are amazing tactile sensors that were developed from Jerry Loeb's lab in USC for prosthetic hands, but can also have been used a lot for robotics. So they basically have a saline-filled fluid chamber surrounded by rubber and electrodes that are doing impedance measurements, spatial impedance measurements, plus a hydrophone, which is like an accelerometer, and a pressure sensor and some temperature sensing. And so we had all of a sudden multimodal tactile sensing, which was really exciting. And but unfortunately, there were some shortcomings. We used them for a ton. I love these sensors. But it's actually pretty hard to interpret these 19 electrodes. They don't have a physical interpretation. It's not really shape. It's an impedance. And it's a compact form, but it only has sensitive area on the outside. If you touch the robot finger on the back, it feels nothing. And they're really delicate. This ribbon cable broke so many times, and these sensors are expensive. They're like $10,000 or $15,000 each. We broke a lot of them, and they're quite difficult to integrate into a platform. And so we had to run the little boards and the wires all down the robot arm. So it was great for research, but not practical for many other applications. And also, this approach for fingertip tactile sensing is clearly not going to work for the whole rest of the robot. And so this project showed me enough that I was really fascinated by tactile sensing and what you can pull out of tactile signals, but that we need better tactile sensors for robots, and that doing that would enable robots to become more intelligent and more capable in their interactions with people. So that is what I'm talking about in this touch sensing to physical human robot interaction cycle. And after all these years of working with lots of different sensors and robots and applications, I can tell you what my wish list would be for tactile sensors. And so my ideal tactile sensors, first of all, it would be soft. And soft is important for cushioning contact and also for allowing a load to be transferred, torsional or frictional load. It's really hard to control rigid contact. So softness is going to be really important. I want to cover my whole robot. I don't want just like tiny little pressure sensors. Something has to hit me right there. That's never going to happen. There can't be dead zones. There can't be blind spots. The whole robot, or almost the whole robot, needs to be covered and tactile sensitive. I need especially, and this is often difficult, to tell the difference between no contact and contact, the start of contact, when something happens, because that means the contact state between the robot has changed. It needs to do something different. Either it's trying to form that contact or it's not, but it needs to know something new has happened. So I want it to be sensitive. But I also want it to have high dynamic range. I don't want to clip those signals. I want to keep responding as the pressure gets higher and higher. So I want it to be nonlinear in its response. I want it to be fast. Time delays are going to be no good. It has to be quick so that I can compensate for what's happening and react, whether it's a high five or something I'm crashing into or something that's falling. We need to respond quickly. It needs to provide useful information. And this is kind of obvious, but what is useful really depends on the task, the part of the body, what you're trying to do with that robot. And I think too often we think of touch sensing as similar to our eyes. We want like a detailed, high resolution, like pressure sensor, like I'm going to press into shapes and identify what they are. And that's often not what we want. Maybe I do need that detailed pressure, distribution, shape. Maybe I need shear, maybe I need slip, maybe I need just contact. Generally, contact happened, the frequency components of contact, that it's warm or cold. It depends on the application, what is going to be useful, which part of the sense of touch we should be focusing on. We absolutely need sensors that are robust and reliable. Robots are going to crash. We need a lot of repetitions, especially if we're going to do anything with learning-based methods. They're going to hit things. Our sensors are going to break. They need to be pretty robust. Softness also helps there. They need to be reliable. So even if it's not going to physically break, if it's computationally disconnecting or the wiring has to be rock solid, and that's a very difficult engineering challenge. Has to integrate easily with my robot, means it can't take up that much space, and they need to be low cost and accessible. And I like sensors that we can just design and build on our own and really understand how they function, that you don't need a PhD to understand the principle, or maybe you do, but if you can implement it just as an undergrad, a bachelor student, that would be, to me, really great. So I selected from our research 4 projects that I think embody different aspects of these goals. They're all very current work published within the last year or two. And I'll tell you about each of them in turn. On the left, we'll start with Insight. This is definitely more like fingertip, high resolution sensing, all the way to HuggieBot, which is much more broad, spatial, and focused on human interaction. And we'll just go through them one by one. So first, Insight. I'll start each project by showing the team. Team is really, really important to me, and highlighting the person who's leading the project. And in this case, it's Juan Bo Sun, who's a PhD student with my close collaborator and friend, Georg Martius, in my institute. And together we wrote this paper that was just published a couple of weeks ago in Nature Machine Intelligence. Georg and I also together have a new PhD student, Iris, who started about a year ago and is continuing this project. And Georg and Juan Bo have done lots of other cool stuff on tactile sensing, so you should look at their work as well. But I'm just going to focus today on this project that we did together called Insight. And Insight is a haptic sensor that is powered by vision and machine learning. And this is not biomimetic at all. We're using a camera to do touch sensing. Why? Well, there are a lot of great cameras available because of cell phones. They're cheap, they're robust, they can acquire a lot of data all together. They're small form factor. And what we do is we have this camera that's looking inside a device that's about the size of a human thumb. And it's a soft elastomer shell overmolded on a stiff skeleton. And it's lit up from the inside. It's opaque, so you see it's silver. And the camera can then see the inside of this hollow shell and figure out where touch is happening. And we can see the whole thing really quickly and then figure out where contact is happening. So I'll explain some of the more details. At every step in time, we take a picture, and pictures from Insight look like this. There's red, green, and blue LEDs, and we're seeing the inside. It's kind of corrugated elastomer. If something is touching, you can see little deformations there. We subtract a reference image, what it looks like when there's no contact, and then we pass that through a ResNet, and it outputs a force map. And this is a 3-channel, so XYZ force distribution of little vectors. And I'll show that this is like all these little points along the surface of Insight. At each point, we can estimate in real time the force vector of contact that's happening there. And you can see it has direction and the distribution of the pressure. And I think this is going to be really useful for manipulation and human-robot interaction. We haven't gotten to that yet. That's what Iris is working on for her PhD. I'll tell you what we think are the 4 key design components of this sensor. First, the mechanics. We need this soft elastomer skin so that it's sensitive, so little deformations cause something that can be seen by the camera, but it has to be strong. And this frame can withstand 40 Newton forces from all different directions. So we get this nice hybrid where we get a response, but it doesn't collapse, or it can maintain structural integrity. The lighting was also more important than we imagined at the beginning. We have 8 LEDs, a collimator shapes the beams so that we illuminate the whole inside well. And we're using photometric stereo and structured light. Both of those principles allow the deformations to be visible to the camera. And then we need a big data set. This is supervised learning. We would like to get away from supervised learning in the future, but for now we have a test bed. I'll start the video. The sensor is sitting on a stand, and it rotates and presents the right side, and then the test bed comes and presses down in and laterally and applies different force vectors, and we collect. You can see here the deformations are happening. In this picture, you can see we do all these little force vectors and are capturing frames and then feed that into the training data. So we have to capture, it takes a few days, I think 3 or 4 days to capture all the data where it's just pushing and pushing. And then we use deep neural networks. And this is definitely more Garrett's domain than mine, where we train end-to-end from these images all the way out to the force map end-to-end, and it learns, I see an image, I can tell you what the distribution of force is for what the contact is happening. And it together works really, really well. So as this is slowed down, so you can kind of look from here where Juanbo is touching the sensor to here, our reconstruction, and this is more internally what the camera is seeing and what the neural network is predicting before we're visualizing it. Maybe I'll just jump to, there's some time later so you can see it. We can see multiple contact locations. You can touch with multiple fingers at the same time and see the directions of contact, including shear, normal force. So it works really well. And we're really excited about this and want to keep building on it. Of course, we took inspiration from lots of other camera-based force or tactile sensors, but we think this is kind of a special, different approach. We were able to achieve an overall spatial resolution of 0.4 millimeters and 0.3 newtons in force magnitude accuracy, root mean square. The forces we can detect with a direction accuracy of about 5 degrees. And we were actually really surprised and excited to see that Insight can feel its own orientation relative to gravity, because gravity pulls the soft elastomer slightly in a different direction. And so it can even feel its own pose. Yeah, so we're going to keep working on this and make it smaller and faster and easier to integrate with robots, and hopefully then do things with robots and stuff and people. So keep watch for more things in that direction. So that was Insight. Next, we're going to move to this ER-TAC, electrical resistance tomography tactile sensors. This project is led by Hyosang Lee, who used to be my postdoc and my research scientist. He's still part-time in my team, but he started in October as a group leader at the University of Stuttgart. And this was a collaboration with Professor Kim at KAIST, also Georg Marcius and other people from my team in Jim's lab in KAIST. We've published many papers over the last few years. I'm just going to tell you about, I'm going to show you just our first big journal paper on the idea, and I'll tell you at the end a little more of other things that we're doing. We wanted to make a scalable approach, a new scalable approach to tactile sensing, not now at fingertips, but maybe on forearms or other areas. And what you might imagine is just, well, don't use a camera. It's not going to work that well for broad areas. You might think to make like little pressure cells, but the problem is that we need a lot of those, and we need a lot of wires coming back, or a lot of interconnections. And we wanted something that was fewer electrical wires for the area that we could cover. And so we created an approach where we have a piezo-resistive material where when it locally gets deformed, the resistance changes there. And we intersperse it with electrodes that we do have wires coming back from. And then the principle is that we can choose any pair of electrodes and we actually scan across to different pairs. And let's say we pass a current between one electrode and another, and that creates a voltage distribution. And then we measure that voltage distribution and we scan all the way across the surface, like the part of the robot's body, and we can reconstruct how the voltage was distributed. And because the material, the skin, is piezo-resistive, that means we can reconstruct the distribution of pressure across the robot's skin. And what is inside this material, what we built, are these low resistance, basically very conductive patches on top of high resistance fabric. And so when there's no contact, the contact resistance between the top layers, the conductive patches, and the lower is high. And so the current, when we pass that current through, it just has to go through the high resistance fabric. But then when someone pushes down in a region, like the robot's bumping its arm into something or someone's pressing on it, that contact resistance goes down very quickly. It's nonlinear. And then locally, the current can jump and flow through these patches and get a low resistance region. And that's distributed all across. We have lots of these little patches and lots of electrodes. And then all together, it gives us this structure. So this is how it looks when it's fabricated. We use a laser cutter to cut the patches and adhesive to put the layers together. We sew the circuitry with conductive thread. We use electronics to scan through the different pairs and gather this data at a very fast frame rate, usually on an FPGA. And then we do the math in real time to do this electrical resistance tomography, basically reconstruct the resistance across the surface. And this is definitely taken from like medical imaging. The voltage measurements to the conductivity distribution we base on physics. And then to calibrate from the conductivity to pressure, we do some simple measurements to get a field of how, because this depends more on the manufacturing and the materials. And we also have done a lot on figuring out what is a good scan pattern. Not any pair, some pairs aren't very good when they're close together. They don't give you very good visibility, but choosing a more optimal scan pattern over time is also interesting. In the end, we've been able to show that we can get very low localization errors, so root mean square down to like 8 millimeters across a really big area. It's like 20 centimeters by 20 centimeters. Pretty good 2-point discrimination, similar to the stomach or the back of a human. And good, it's important, we're not just doing contact location, but also force. So at every level, we know the pressure. We're estimating how strong. So it's going up the harder you push on it. And I'll just show you the videos because that's probably the most convincing evidence. This is Hyosang pressing on different areas of our sensor. And you can see in real time, the reconstruction shows where he's pushing. And he can push with more than one hand. We did also test without the internal electrodes. The internal electrodes have a big improvement of the resolution, especially in the middle. So I'm only showing that version. You can see 2 contacts. You can't even visually see which one he's pushing on, but the sensor completely knows like how hard he's pushing. And then this right video just shows the impact of the calibration. So we have a constant mass. On the left, we're showing without the calibration. You can see as he moves it to different locations, it doesn't know the pressure. It's just knowing the resistance. And many other teams use this approach, but they don't go all the way to force. And I'm a mechanical engineer. I want actual force. If you push on me with 2 newtons or 3 newtons, I want to know it. I don't really care how much the resistance changed. I really want to know the force, because someday we're going to have a robot wearing the skin and pushing into things and wanting to control those interactions. So that was this paper that we published last year in Smart Materials and Structures. As I said, we've worked on various aspects of the project. It's really led by Hyosang. We've also done adaptive optical measurements and using deep learning and simulation to reduce the amount of real data that we have to collect and improve the accuracy. But I think I'll stop talking about this now and move on to the third project, which is called HERA, the haptic empathetic robot animal. And this project is led by Rachel Burns, one of my PhD students. Hyosang is also involved, as is Hasti Seifi, who was my former postdoc and is now an assistant professor at the University of Copenhagen. So far, we've published 2 papers. The first, we interviewed autism specialists and got a lot of input on what they might imagine for touch sensing for a robot to help children with autism. And then this most recent paper, which was just accepted a week or 2 ago to Frontiers in Robotics and AI, on endowing a now robot with practical social touch perception. I'm just going to tell you about this part of the project, which is about the sensing. So Rachel's overall goal is to create a robot, a haptic empathetic robot animal that can help children with autism learn more safe and appropriate touch behavior. And now a robot on its own, they're very commonly used. They're little humanoids that are often used with children with autism and lots of other educational activities, but they have almost no touch sensing. They have just little capacitive touch sensors on their hands and their head and foot bumpers. So we have built a tactile perception system that we can install onto now, and now also wears a koala suit, and then we're working on its emotion response system. But today I will just talk to you about its tactile perception system. So we use a very simple resistive-based tactile sensor. We have a top electrode, low conductivity foam, and another electrode, and that just acts when pressure happens. It just reduces the resistance. We put it in a voltage divider. Here we're not doing contact location at all. So each sensor is monolithic and has just one taxel. We want to cover the robot's whole body, and something that's practical and that a therapist could use, and it will be robust. So I have a video that I'm going to show. This is showing a little bit about how we make them. One thing is important to note, here's some photographs. The layers that we build, there's a bottom layer of foam, and then a conductor layer, and then the low conductivity foam, and then another conductor. That's that sandwich. In the beginning, we would make them flat, like you see here. Then we would bend it onto the robot, and it would totally not work because that bending deforms the foam and pre-stresses the sensor. And so now we've learned to make the sensors so they fit around and are not stressed from the beginning. And I'll show you how we make these tactile sensors. And also with this paper, we've released all the patterns for how to make these sensors for the arm of the now. In the future, we'll release the whole body. You assemble your materials, so foam, the non-conductive foam. Someone's unmuted. Is there an issue?
And also from the geographic.
Sorry, I'll keep narrating my video, and if someone else could just see.
Yeah, sorry about that.
Thanks. No worries. At first, I thought it was the video. So you see how we're cutting the different pieces and putting them together, and it's very important to see how the internal layers that will be closest to the robot's body are smaller, and that way, when we wrap them around the curvature of the robot's body, they all line up and aren't pre-stressed. And then we heat fuse them either with a hand iron, or this is a mug press. This is how they put designs on coffee mugs. And we get this pre-curved 3D one taxel sensor per body segment for the now. And now I'll tell you a little bit more about what we can do with that. So far we've made just one arm, and I'll show you how we validated that. We brought people into the lab and had them touch the robot and to show different kinds of social touch gestures that the autism therapist had told us would be useful. In particular, we had them demonstrate things like stroking the robot's hand energetically, or in a moment, the participant is going to be asked to hit the robot. People actually don't like hitting the robot, but you can watch the real-time data streaming across here. So even though we have only 4 measurements, so the 4 body parts, shoulder, upper arm, lower arm, and hand, we get really nice, rich data in the patterns over time. That's why it's important that the sensor respond quickly, and we get this rich data stream. So we had 15 people come in and touch all 4 parts of the robot's body with these 5 different gestures at 2 intensities, and they did 3 repetitions. We have this big data set that we then parsed. And then did some simple machine learning on basic features using a random forest. We got very good classification rates of just little individual windows of data, knowing like which body part is hit, whether they're at the gentle or the energetic intensity, and that hasn't been studied very much. We're very interested in intensity, and this was our first just 2-level version of intensity, and pretty good at doing the different gestures. It gets harder when you're doing a little bit lower when we're with intensity and gesture at once. But a big part of this is that people don't do the same thing. You say gently stroke, and some people are gentle and some people are a little more violent, and vice versa. So there's a huge variety in what people did. This was very uncontrolled data. So we're really happy with this data set. People also gave very good evaluations of the robot. They weren't afraid of it or threatened by it. They thought it was a good idea and useful. And interacting with the robot significantly increased their appreciation of the presence of the robot. So these are our results just about the tactile sensing capabilities. We're continuing to work on this project, and I'm really excited that we're going to have a now with full tactile sensing all over it and what it can do. And now I'll tell you about the last project that I wanted to describe today. And that is HuggieBot, also a social physical human robot. This project is led by my former PhD student, Alexis Block, Dr. Alexis Block. She finished her PhD at ETH in August. She's now a postdoc at UCLA. And we just heard a couple of days ago the very good news that she won the Otto Hahn Medal. The Max Planck Society, this is our thesis award. They give about 30 of them a year. And I'm really proud of all the work Alexis did in her PhD on HuggieBot. She published, this is a collaboration also with professors at ETH and again with Hasti and Sami. We published many papers, and I thought I would mainly tell you about one that was just accepted a couple of weeks ago to the Transactions on Human-Robot Interaction, which describes what we call HuggieBot 3 and a little bit also of HuggieBot 2. So this is called In the Arms of a Robot. It's about if you're hugging someone and you squeeze them or pat them on the back, we would like robots to be able to do that too. Okay. Why make a hugging robot? You might be sitting there thinking this is an embodied intelligence conference and hugging sounds pretty stupid, but actually hugging is really good for humans. Hugging provides us with social support and strengthens our immune system, increases our oxytocin levels, and it alleviates stress. Before I came to work this morning, I asked my husband if I could get a big hug because he knew I was doing this talk. It has a tangible physiological improvement, social contact and hugging, deep pressure touch. And when we don't get enough hugs, which might have happened to you, like it happened to me in the pandemic, we become more at risk for depression or other mental health problems. Our pain thresholds go down. We have lower self-esteem, and we may have more trouble forming relationships, especially babies or children who don't have touch in their lives can struggle socially. And so people have created hugging robots before, and there were two main categories of hugging robots we found in the literature. One is these big, like animal-like robots that sit on the ground. It's mostly for children. You have to crawl over to them. And also a lot of smaller, very impressive, more like pillow-sized robots. But especially these, they don't hug you back. You hug them. They're a sensor. They can feel. They might talk to you, but they don't physically hug you back. And that physical contact, that physical squeezing back, is known to be really important. And so in the middle are more human-sized anthropomorphic hugging robots. And we're especially interested in autonomous robots. For her master's thesis with me, Alexis made HuggieBot 1.0, which is the same PR2 you already saw in a purple furry outfit with heat. And this was published in IJSR a few years ago. And people did like hugging the PR2 much more than we imagined. And that convinced us to do Alexis's whole PhD on hugging robots. But this platform had a lot of shortcomings that we addressed by building a full new platform that I'll tell you about now. Over the course of Alexis's PhD, we created 11 design guidelines or commandments for hugging robots that we hope can generalize to other robots beyond ours, and also just generally to helping robots or robots that are going to work around people. 5 of them, these 5, I'll highlight in terms of HuggieBot 2.0. And this was published at HRI last year. This is the International Conference on Human-Robot Interaction. I'll just play the video while I narrate so you can watch people hugging our robot. So the robot has a V-shaped frame that lets you walk up close to it. It has 2 Canova Jacko padded arms, heating pad, an inflated torso, soft clothing, a screen so it can show you its face, and it has a camera so it can see you. And it's really nice and huggable. It's soft and warm. It's human size. It's the size of an adult human. And it adjusts to you. If you're bigger or smaller, you're over to the left or the right. It's basically closing like a hand would grasp an object. It's like a big 2-fingered grasper, but it's a hugging robot. And it stops when it feels you. And when it feels that either the pressure in the back has lowered because you've let go, or an increase in the torques because you're leaning back, it lets you go and you can end the hug. People really don't like it if the robot hugs too long and doesn't let you go. You have to let the user go. We don't want to stress people out. So this was HuggieBot 2.0 from last year. And it's very fun to hug. There were a couple of shortcomings though. One of them was the vision. We hadn't in the beginning estimated the user height. And if you're very tall and the robot hugs you at the same height, it will be hugging you around your butt. If you're very short, it'll hug you around your neck. And so taller and shorter people didn't like being hugged by the robot as much. So obviously the robot should see you and adjust to how tall you are. And it should also synchronize, like when it opens its arms and when it closes to your approach. I'm not going to talk more about that, but those were very important to improve. But the main thing I want to talk about is these intra-hug gestures while you're in the arms of the robot. And this is this paper in Transactions on Human-Robot Interaction. So here you can see I've taken the clothes off the robot, so you can see this inflatable, we call it Huggy Chest. This is just made from like a beach toy, pieces of vinyl, inflated, and with a microphone and a pressure sensor inside. And that's what forms the torso of the robot. And we don't have distributed tactile sensing. We have a single microphone and a single pressure sensor in the back chamber. And for this study, we defined 4 gestures: just holding the robot, squeezing it, rubbing your hand, and patting it. So sort of just pressing in, lateral motion, and impacts. And here's some sample data of different participants in a data collection study that we do. What you can see how the robot feels on the pressure sensor and the microphone, what it feels like to the robot to be held, squeezed, rubbed, or patted. Everyone does things differently. Some people are very violent when they pat. Other people are much gentler. Some people squeeze over and over. They do all sorts of things. They wrestle around. So we collected a big data set. We again use real-time machine learning on little windows of data to recognize what the user is doing. Can do it pretty well. And then even more interestingly, how should the robot respond? And so when you're in the arms of the robot and you do something, how should the robot respond? This is like the intelligence part of the robot. So we did a study where we tested all possible pairs of the 4 actions a user could do and the 4 ways a robot could respond. So each person had 16 trials in random order, and they had to tell us what they thought. And higher is better. And I'll walk you through the spot. First of all, people really like it when the robot responds to something, whether the robot responds with a rub or a pat or a squeeze. They really like that the robot does something in response to them. The only thing they don't like is when they do something and the robot does nothing. So you're holding the robot, you pat it and it stays still. Many people think this is a rude robot. Surprisingly, people really liked it when they were holding still and the robot proactively rubbed or patted or squeezed. People especially love being squeezed. Squeezing is very comfortable. It comes back to deep touch, deep pressure touch. And so people just generally really liked it when the robot did stuff, but it was important that the robot feel when they do something. We had initially hypothesized that the robot should do what the user did, but that wasn't at all what we found. Instead, people want the robot to be more creative. So we programmed a probabilistic behavior algorithm for the robot to decide based on preferences, like preferentially choosing more favored responses, but not being predictable. And now here's a participant in our study. The robot says, "Can I have a hug, please?" And he walks in, it sees that he's a tall guy, and now it's closing in, and it's collecting a baseline pressure reading, and now he's holding still, and the robot knows that. And now watch I think it's this hand here, he's about to pat, and the robot feels he's patting, and the robot rubbed him in response. Now the robot is squeezing him, now he's squeezing it, the robot feels that he's squeezing, now he's patting again. And then you have this intimate interaction. I know it's hard to see, you can sort of see the robot hand here. Now the robot's like, he wants to let go. He's done with his hug. But we tested a lot of people in these hugging interactions. And it's really actually very fun. Our robot can detect and classify these gestures, respond very quickly. It's proactive and doesn't feel robotic. Here I'll play, this is another participant, and then just along the bottom, you can see this is they hug the robot a couple times at the beginning and a couple times at the end of the study. And these are their impressions of how natural the robot is, how enjoyable it is to hug, how intelligent the robot seems, and how friendly. We saw significant improvements after these hugging sessions, except in friendliness, but the robot got very, very high friendly ratings at the beginning. So overall, I wish I could let all of you hug Hugibot. I think you would enjoy it much more than you imagine. And you would believe me more than me just showing you videos of happy people hugging and squeezing and rubbing a robot. But we think this is actually something that could provide a benefit to people, not to replace human hugs, but to supplement them for times when a human hug isn't available. So that is Hugibot. And if you want to learn more, this paper is on arXiv. It's not yet on the THRI website, but you can find it on arXiv. And there will be more in the future as well. There's one more chapter of Alexis's thesis that we haven't published yet. So that's the 4th project, Hugibot. And I know it was a whirlwind, but those were the main things I wanted to tell you. And now I've hopefully given some credibility to the hopes that I wanted touch sensors to have. These are some directions that we're going. Maybe a few overarching ideas you might have taken out. I think the sense of touch is important for robots, for people. I don't think it gets enough attention. It's multimodal. It has many different channels. We don't understand it very well yet. robots need to have in their sense of touch broad spatial sensitivity and high temporal bandwidth. It doesn't work just to have one little touch sensor in one place. We can use individual sensors that have high bandwidth or broad receptive fields to instrument large robot parts. I think this hasn't been tested very much, and I think it has a lot of promise. And any algorithm that we're running has to be able to work in real time, so the robot can respond very quickly to whatever the human or the object has done or has happened. So that's my team from recently. I want to close by thanking you and the organizers and everyone who has supported this work in different ways. And with that, I'm happy to take any questions or comments.
Thank you so much, Catherine. That was a really fantastic talk, touching on so many different areas. And I love your wish list for tactile sensors and the work on HAPTIC as well. I think is so interesting to show how we can use these sensors as a means of communication between humans and robots. So please do put any questions in the chat, and we can get those to Catherine through either the Discord or the chat. One question I just had was, you introduced this really interesting idea of describing the outcome from touch sensors as adjectives or heat maps, or creating a language in which we can analyze and interpret tactile sensors. I just wonder if you could talk a little bit more or give you your thoughts on, is there one fixed language, or is it something that's flexible?
Oh, no, there's definitely not one fixed language. In that HAPTIC adjective project, we had a fixed set of objects, and we brought people in and had at least 4 people touch every robot and then choose from a vocabulary of adjectives. And there was a huge variability. Actually, we have a few papers on that data set also describing the variability in perception. There isn't just one label. There's different interpretations or different, someone might say this feels nice and someone else might not. So modeling like a population's impression. Understanding the sources of variability in human tactile perception is something that I'm really trying to understand, both for haptic rendering and for things like this. Like, why does it seem more varied than, say, the human sense of vision? Half of it, I think, is that we can't capture haptic interactions as well as we can capture visual or auditory stimuli. And when we're capturing them, we're often disturbing the interaction. So, but in general, we often, there is no one vocabulary, and we need to capture a distribution of descriptions and kind of proceed in that way. That's my impression.
No, that's really fascinating. And I think it's interesting how often we capture tactile information that aids us as humans, but that's not necessarily an optimal, or we find a visual representation that makes sense to us as a data analyst rather than actually an optimal information. And another question related to something in the chat about HAPTIC. Do you think there's a learning aspect? So the robot is starting to learn something about the humans. Do you think, to what extent does that exist? And also, do you think the humans start to understand the robot's behavior or its sensory capabilities and behave accordingly?
Yeah, no, people definitely, the more times they hug the robot, the more comfortable they get. It's like sitting in a massage chair. In the beginning, it feels weird, and then you kind of understand, and like, how do I use this to make myself feel good? So far, we haven't done a deep analysis. The robot is not actually learning over time. It has a static representation of the gestures and has a fixed control algorithms for how to close onto people. We know how big people are, like it could, but I think that's not a very interesting thing, and how they approach. We have lots and lots of data. We have an intern coming this summer who may delve more into these topics, but what we really want to do is actually take HAPTIC out into the public. We're going to exhibit it at the Stuttgart Science Festival and maybe also at EuroHaptics in Hamburg, and let more people hug HAPTIC than just the people who volunteered for our studies during COVID, and think about what would the next generation of hugging robots be, and how can this robot better support people.
Perfect. And we do have quite a few questions in the chat, but I'll just finish with one before we go on to the panel speakers, but then also we can get you back later, hopefully, to ask you a few more things. I was just wondering about the role of morphology, because you touched on this, I think, with the EIT-based sensors, how you can optimize its morphology. How do, even in HAPTIC, for example, how critical do you see morphology in the sensory interaction with humans, or in the learning, and should that be central to our design of sensors?
No, morphology is definitely important, and we're basically just, it's such early days, in my opinion, with adding tactile sensors to like moving robots, that we're like creating a system and then we're going to learn from it and hopefully be able to generalize more in the future. But for HAPTIC, in the beginning, we put a microphone and pressure sensors in both the front and the back chambers. And there was basically no useful information in the front, because the person's hands are naturally in the back, and that's where they're acting and moving and letting go. So I always want simple sensors, like as simple of a system as possible. Now, could we apply like insight, camera-based, looking inside the robot? Sure, I think some other people have started to go that direction, but we wanted really simple, really robust, and kind of all surfaces. And it worked surprisingly well. No matter where the user puts their hands, no matter where they're patting, we can get a pretty good impression of what's happening. But that is just for this application of hugging. Like if it's going to be working next to you, you're going to want to be able to pat the robot on the shoulder, or if it bumps into you, that's more the now based, the third project that I showed here, where we have lots of rigid robots and we want to cover them with tactile sensing that would be specific to body parts.
Amazing. Thank you so much for your talk again. And we really will follow up with those questions. Thank you for everyone in the chat.
My pleasure.
And I think also your wish list for tactile sensors, I think we can very much put that out to everyone. I think that's fantastic. I think that gives us many of goals to work on in the coming years. So thank you once again.